Hello everybody, I am Professor Yogesh Chaba from Guru Jambeshwar University of Science and Technology, Hisar, Haryana. Today in this lecture, we will study about Data Encryption Standard DES. This lecture on DES has been divided into three parts: Introduction, DES algorithm and modules of DES. In early 1970s, the US National Bureau of Standards NBS recognized that the general public needed a secure encryption technique for protecting sensitive information. Historically, the US Department of Defense and the Department of State had great interest in encryption systems. It was thought that these departments were home to the greatest expertise in cryptology. However, precisely because of the sensitive nature of the information they were encrypting, these departments did not release any of their work. Thus, the responsibility for a more public encryption technique was delegated to the National Bureau of Standards NBS. To allow the algorithm to be public, NBS hoped to reveal the algorithm itself. In 1972, the NBS issued a call for proposal for producing a public encryption algorithm. Very few organizations responded to the call. So, the NBS issued a second announcement in August 1974. In response, the most promising suggestion was the Lucifer algorithm, on which IBM had been working for several years. The data encryption algorithm proposed by IBM for National Bureau of Standards was known as the DES, Data Encryption Standard. Its proper name was DEA, Data Encryption Algorithm in United States, and DEA-1, Data Encryption Algorithm 1 in other countries. National Bureau of Standards called on the Department of Defense through its National Security Agency to analyze the strength of the encryption algorithm DES proposed by IBM. Finally, the NBS released the algorithm for public scrutiny and discussion. The DES was officially adopted as a US federal standard in November 1976. Eventually, DES was accepted as an international standard by the International Standards Organization ISO. DES is symmetric key algorithm because it uses the same key for encryption and decryption. Figure as shown illustrates the use of a symmetric key algorithm. Encryption key is applied to plain text P so that ciphertext C is produced. On receiver side, same key K is applied on the ciphertext to decrypt the text, and thus plain text P is produced. Transpositions and substitutions are used in DES. Transpositions or permutation means changing position of bits. Substitution means replacing bits. Figure A shows a device known as a P box, which is used for transposition on an 8-bit input. If the 8 bits are designated from top to bottom as 0, 1, 2, 3, 4, 5, 6 and 7, the output of this particular P box is 3, 6, 0, 7, 1, 2, 4 and 5. By appropriate internal wiring, a P box can be made to perform any transposition. Figure B shows substitutions are performed by S boxes. In this example, a 3-bit plain text is entered and a 3-bit ciphertext is output. The 3-bit input selects one of the 8 lines exiting from the first stage and set it to 1. All the other lines are 0. This is substitution. The second stage in this diagram is a simple transposition. The third stage encodes the selected input line in binary again. In DES algorithm, combination of transposition and substitutions are used. The strength of the DES algorithm derives from repeated application of substitution and permutation one after other for a total of 16 cycles. That is, plain text is affected by a series of cycle of substitution and permutations. The iterative substitutions and permutations are performed as outlined in figure shown. Plain text is encrypted in blocks of 64 bits yielding 64 bits of ciphertext. The algorithm, which is parameterized by a 56-bit key, has 19 distinct stages. The first stage is a key independent transposition on the 64-bit plain text. The last stage is the exact inverse of this transposition. The stage prior to the last one swaps the leftmost 32 bits with the rightmost 32 bits. The remaining 16 stages are functionally identical but parameterized by different functions of the key. The algorithm has been designed to allow decryption to be done with the same key as encryption, a property needed in any symmetric key algorithm. On the decryption side, the steps are just run in reverse order. Now, let us see this algorithm in detail. Input to the DES is divided into blocks of 64 bits. The 64 data bits are permuted by a so-called initial permutation. The 64 permuted data bits of stage 1 are broken into a left half and a right half of 32 bits each. The data bits are transformed by a key. The key is shifted left by a number of bits and permuted. The key is combined with the right half, which is then combined with the left half. The result of these combinations becomes the new right half, and the old right half becomes the new left half. The cycles are repeated 16 times. After the 16th cycle is a swapping operation and final permutation, which is the inverse of the initial permutation. Remember here that permutation and transposition are one and the same thing. Now, we will see in detail working of each cycle of algorithm. There are 4 separate operations in each cycle. First, a right half is expanded from 32 bits to 48 bits. Then, this expanded right half is combined with a form of the key by an exclusive OR function. The result of this operation is then substituted for another result and condensed to 32 bits. The 32 bits are permuted and then combined with the left half to yield a new right half. Old right half now becomes new left half. Now, let us see how 32 bits are converted into 48 bits by expansion permutation. The expansion has two purposes. First, to make the intermediate half of the ciphertext comparable in size to the key, and second, to provide a longer result that can later be compressed. Each right half is expanded from 32 to 48 bits by means of the expansion permutation. The expansion permutes the order of the bits and also repeats certain bits. The expansion permutation is defined in the table. For each 4-bit block, the first and the fourth bits are duplicated, while the second and the third are used only once. This table shows output position to which the input bit moves. Since this is an expansion permutation, some bits move to more than one position. Each row of the table shows the movement of 8 bits. As shown in table, bit 1 moves to position 2 and 48 of the output, while bit 2 moves to position 3. Bit 3 moves to position 4. Bit 4 moves to position 5 and 7. Bit 5 moves to position 6 and 8. Bit 6 moves to position 9 and so on. Now, let us see how key is transformed in each cycle. The 64-bit key immediately becomes a 56-bit key by deletion of every 8th bit. The key is reduced from 64-bit to 56-bit by dropping 8th, 16th, 24th, 32nd, 40th, 48th, 56th and 64th bit. These bits are parity bits that carry no information in the key. At each step in the cycle, the key is split into two 28-bit halves. The halves are shifted left by a specified number of digits. The halves are then pasted together again, and 48 of these 56 bits are permuted to use as a key during each cycle. Key is reduced to 48-bit by not selecting 9th, 18th, 22nd, 25th, 35th, 38th, 43rd and 54th key position out of 56-bit key, thus reducing key to 48 bits. Now, let us move on to substitution process performed by S boxes. Substitutions are performed by 8 S boxes. An S box is a permuted choice function by which 6 bits of data are replaced by 4 bits. The 48-bit input is divided into 8 6-bit blocks identified as B1, B2, B3, B4, B5, B6, B7 and B8. The S boxes are substitutions based on a table of 4 rows and 16 columns. Suppose that block B1 is a group of 6 bits B1, B2, B3, B4, B5, B6 as 1, 0, 1, 1, 0, 1. Bits B1 and B6 taken together form a 2-bit binary number B1, B6 as 1, 1 having a decimal value from 0 to 3. Call this value R, which is 3 in this case. Bits B2, B3, B4, B5 taken together form a 4-bit binary number B2, B3, B4, B5 having a decimal value from 0 to 15. Call this value C, which is 6 in this case. The substitutions from the S boxes transform each 6-bit block B into a 4-bit result shown in row R and column C of section S of table. For example, block B1 is 101, 101, then R is equal to 3 and C is equal to 6. So, the transformation of block B1 is found in row 3 and column 6 of section 1 of table, and this value is 1. The value 1 is equal to 0001 in binary, which is substituted for the value 101101. This is how substitution is performed. After an S box substitution, all 32 bits of a result are permuted by a straight permutation box P. Table shows the position to which bits are moved. 8 bits are shown on each row. For example, bit 128 of the output of the substitution moves to bit 9th, 17th, 23rd, 31st, 13th, 28th, 2nd and 18th position. Similarly, bit 25 to 32 moves to 32nd, 12th, 22nd, 7th, 5th, 27th, 15th and 21st position. Now, let us move on to initial and inverse permutations of stage 1 and 18. The DES algorithm begins with an initial permutation that reorders the 64 bits of each input block. The rule for initial permutation is shown in table. As we can see in the table, bit 128 goes to position 40, 8, 48, 16, 56, 24, 64 and 32 respectively. Similarly, bit 25 to 32 goes to position 37, 5, 45, 13, 53, 21, 61 and 29 respectively. In this way, 64 bits of data is initially transposed. At the completion of the 16 substitution permutation rounds, the DES algorithm finishes with a final permutation by inversing initial permutation in stage 19. So, this was DES algorithm. Now, to summarize, let us put all the pieces back together for DES algorithm. First, the key is reduced to 56 bits, then a block of 64 data bits is permuted by the initial permutation. This 64-bit permuted data is divided into two parts. Then permutation and substitutions are performed in right 32 bits. The result is combined with the left half of 32-bit data block. This operation is repeated 16 times. Then left and right parts are swapped, and in last the data block is permuted with the final permutation. So, dear friends, this was all about DES algorithm. Thank you.